Swayam Prabha. Digital India. Educated India.
Hello everyone, a very warm welcome to all of you in this course. So this is the third. Hello everyone, so welcome to this second lecture of third part of the lecture series of mineralogy. And in this second lecture, we will mostly learn about the crystal chemistry and what kind of minerals are present in the Earth's mantle and in the crust, and and their structure, and we will also discuss some of the physical properties. So, if you remember, in the last lecture we discussed several things, and first we discuss about the definition of the mineral, and then from that we try to understand what are the most abundant mineral in the crust and in the mantle. And if you remember the diagrams, most abundant element in the crust and mantle, so you will find that the three most abundant mineral in the crust is your oxygen, silicon and aluminum. And if you combine these three most abundant elements in the crust, so you have almost a 82 weight percent. Okay. When you go to the mantle, so in the mantle you will see that the order is changed, and the three most abundant element in the mantle are your oxygen, magnesium and silicon. And if you combine these three elements, you have almost a 95 weight percent of these three elements which is present in the mantle. So, if you see the abundance of the element in the crust and the mantle, because they are abundant in different minerals, so their mineralogy is completely different. We will discuss about this in the next slide. We also discuss the most abundant element in the crust and mantle, and what are their charges, valency, and what are their coordination number, and what are their ionic radii. So, this we discuss in detail. Then, because we have the two most abundant element in the crust and mantle is your oxygen and your silicon. So, you see in both the case you have a oxygen and silicon which is quite abundant in your crust and mantle. So, most of the minerals form is made up of this silicon and oxygen, and basically they make a silicon tetrahedron, and this silicon tetrahedron have at the center you have a silicon atom which is connected with 4 different oxygen. And because at the base of the tetrahedron you have a 3 different. So, if you draw your tetrahedron, and if you draw the base of the tetrahedron, so basically you have a 3 oxygen at the base of the tetrahedron. So, you have 2 minus, you have oxygen 2 minus, you have oxygen 2 minus. So, if you see the base of the tetrahedron, and if you want to connect the another tetrahedron from the base and you want to combine, so what you will find that the base of the tetrahedron has a net charge of minus 6 minus. So, basically the charge is quite large at the base of the tetrahedron, and if you see the vertex where you have only one oxygen atom which has a minus 2 charge. So, you can easily combine another tetrahedron from this side. So, from this side, but if you want to combine the tetrahedron from the base, because the charges are large, so in that case there will be a repulsion, and it is not possible that we can combine these tetrahedron from the base. Okay. So, this is in nature we do not find this kind of scenario where the two bases of the tetrahedra are connected, but you find the oxygen which is present at the vertex of the tetrahedron that are connected. So, when you have this kind of situation, this oxygen is called as a bridging oxygen, and all other oxygen which are not connected with other oxygens in the crystal structure, that are non-bridging oxygen. We also discuss little bit about the bond length of silica oxygen, which is, if you calculate and if you experimentally determine. So, what we will observe that these bond lengths are slightly shows a lesser value than the what we will calculate from the theory, and that is because of the some kind of covalency is present in the most of the silicate structure, which we will also learn in this class. And if you see the bond angle between a silica oxygen and silica, so that is almost 140 degree. And we also discuss how to write down the mineral formula, and we discuss also different type of silicate structure, disosilicate, inosilicate, and different silicates, and what are their structures, and what are the minerals can be present in these kind of structures. So, this we learn this in detail, and if you see the most common mineral which is present in the your earth crust. So, this is defined in this diagram. So, if you see this diagram, so what you will observe that, and these numbers are basically showing a volume percent. So, whatever number is here, these are basically your volume percent. So, if you see the crust, so in the crust you will find that plagioclase is almost 39% plagioclase is present, and if you see the alkali this feldspar, that is almost you have 12%. So, if you combine these two feldspar which is present in the earth crust, so that is almost more than 50%. So, if you combine, it is a 51 volume percent of feldspar is present in the earth crust. Why you have a 51% of feldspar in the earth crust? Mainly because if you see the most abundant elements in the earth crust, so that is you have oxygen, silicon, aluminum, and calcium and iron. So, all these minerals, this feldspar have aluminum, calcium, iron, all these minerals are present in the feldspar, and because of that you have two most abundant elements, two most abundant minerals in the earth crust is your plagioclase, and you have your this feldspar, alkali feldspar. And if you see the third most abundant mineral in the earth crust, that is your quartz, and quartz is almost 12 weight percent is present, and the fourth most abundant mineral is your 2-pyroxene, that is your orthopyroxene and clinopyroxene, they combine together, and almost 11% is pyroxene is present. So, if you see all these minerals, okay, so these minerals are mostly made up of your these minerals are mostly made up of your silicon, aluminum, calcium, magnesium. So, magnesium is less in your crust, because of that you have a very small amount of pyroxene. So, basically in the crust, most of the minerals which are present in the your earth crust are rich in different elements, that is your aluminum, silicon, and calcium and iron. So, these minerals are quite abundant in the earth crust. If you go to the mantle, which starts from 30-35 kilometer beneath your continent, sometime little bit deeper, or beneath the ocean, it is 10 to 11 kilometer. So, if you see the mantle is divided into 3 parts, 3 layers. So, the upper layer is known as your upper mantle, and this upper mantle is basically from your whatever you have a crust mantle boundary in continent or in the your ocean, beneath ocean. So, from that for example, you have a 30 kilometer, and then it will upper mantle will be up to a 410 kilometer. So, this is your upper part of the mantle, and then you have a second layer in the mantle, which is called as a transition zone. So, transition zone starts from 410 kilometer to your 660 kilometer depth. This is the transition zone. Then you have a third layer, the bottom layer, which is known as a lower mantle, and lower mantle start from 660 kilometer to your 2900 kilometer. So, basically broadly the mantle is divided into three different parts. The upper part is known as the upper mantle, and then you have a middle part, that is a transition zone, and then you have a third part, that is your lower mantle. And if you see this diagram, this right hand diagram in this presentation, so it basically indicates what are the minerals stable in the earth's mantle in with at different depths. So, if you see this diagram is only applicable when you consider the earth's mantle is made up of your ultramafic rocks. Okay. What is ultramafic rock? So, ultramafic rock is the rock which is made up of a mafic minerals. So, mafic minerals is the mineral in which you have lots of magnesium and iron. For example, if you write down some example for the mafic mineral. So, for example, olivine. So, olivine is formula is MgFe whole twice SiO4. So, this is your mafic mineral. There is another mineral like pyroxene. You can write down the formula of pyroxene. So, in the pyroxene, suppose if you take a pure Mg end member instatite. So, you have a Mg 2Si2O6. So, these minerals are made up of magnesium and iron. So, if your mineral is made up of magnesium and iron, then we call this mineral as a mafic mineral. So, when a rock is made up of more than 90 volume percent of mafic mineral, we call that mineral, we call that rock as a ultramafic rock. So, this diagram, this right hand diagram which shows the abundance of different minerals in the mantle is only applicable when you consider the mantle is made up of a ultramafic rock, and these kind of information we can basically get from the xenology studies. So, sometimes some foreign materials are coming from the earth's interior, and when you analyze this mantle xenoliths, what you will find that most of these xenoliths are ultramafic in composition. They are precisely they are Lihargolitic or Habsburgitic in composition. So, this is a kind of a peridotite, which is the definition of peridotite is if the ultramafic rock has more than 40% volume percent of your olivine. So, this rock is called as a peridotite. So, in peridotite basically 4 different minerals are present. So, you have a olivine, olivine proportion is always more than 40%. Then you have a 2-pyroxene, you have a orthopyroxene, you have a clinopyroxene, and then you have a less than 10% of some aluminum rich phase, aluminous phase. For example, either you have a plagioclase or you have a spinel or you have a garnet. So, that is your aluminum rich phase. So, that is present less than 10%. So, when you have a peridotite, peridotite have a different name. So, in this part I will not discuss about this, but you before we are going to discuss this figure, you should consider that your mantle is mostly made up of your ultramafic composition. So, if mantle is first assumption is the if the mantle is ultramafic in composition. So, what you will observe that your upper mantle which is from your crust mantle boundary Moho discontinuity to your 410 kilometer, which is from up to this height. So, if you see the volume fraction of different minerals which are present in your upper mantle. So, what you will observe, there are 2 different parts. Okay. So, one part is up to your, if you draw a horizontal line, if you draw one horizontal line. Okay. So, what you will observe that from 30 kilometer to this 10 gigapascal. Gigapascal is basically a pressure. So, 1 gigapascal is equivalent to 10 kilobar, and 10 kilobar, 1 kilobar is equivalent to 1000 bar, and 1 bar is equivalent to 1 atmospheric pressure. So, basically your here your pressure is almost a 50 kilobar. Okay, so you have 100 kilobar. So your 100 kilobar multiplied by 1000, so that is your atmospheric pressure. So if you take this depth at 10 GPa pressure, so this is equivalent to your 300 kilometer. So if you see this part from 35 kilometer to 300 kilometer, what you will observe that there are 4 minerals are stable in this part. So the most part of this upper mantle is made up of olivine. So which is made up of olivine. So you see that almost 60% of the upper mantle is made up of olivine, which is indicated by this olive green color. Okay. So 60 volume percent of the upper mantle, the upper part of the upper mantle is made up of olivine. Then you have almost 10% or little bit when you go deeper, you have slightly more garnet composition. So basically 12% volume percent of garnet is present in the 10 to 12 or 15% of garnet is present in the your upper part of the upper mantle. Then remaining your this remaining 28% or 25% is basically your 2 pyroxenes. Okay? And you will observe that when you cross the 300 kilometer depth, which is equivalent to your 10 gigapascal, you will observe that orthopyroxene is not stable below this depth. So orthopyroxene is indicated by this brown color, dark brown color, and the next green band is define the stability and proportion of clinopyroxene in the Earth's mantle. So you see that when you cross the 300 kilometer, you will find that orthopyroxene is no more stable. So in the upper part of the mantle, you mostly have a olivine rich rock, okay, and 60 volume percent of olivine is present, and then you have a remaining, this part is made up of your 2 pyroxene and garnet, and we know that this olivine is mostly orthorhombic in its structure, and this is a nesosilicate, and then you have a garnet which is a cubic in structure, isometric. So you have a cubic structure. So that is also a nesosilicate. So basically you have a silicon tetrahedra that are isolated. We will discuss about the structure of these phases in the next slide. And then you have a 2 pyroxene, orthopyroxene and clinopyroxene. These 2 pyroxenes are basically your inosilicate. So you have a chain silicate. So these are the abundance of minerals in the upper part of the upper mantle. When you go to the deeper, when you go below 300 kilometer and you go up to a 410 kilometer. So if you see from 300 to 410 kilometer depth, what you will observe that in this band, in this depth, your olivine is still present up to a 60%. Okay? But when you go to this red zone, what you will observe that you do not have a orthopyroxene in this part. So you mostly have a clinopyroxene. So and also when you go deeper and deeper, for example, if you draw one horizontal line at 410 kilometer, so what you will see that the proportion of your clinopyroxene, which is present almost like a 15% or 12%, this is decreasing when we go to the base of the upper mantle. So, now it is almost like a 5%. So, what exactly happens here, that when you increase the pressure and when you go from 300 kilometer to the 410 kilometer, your clinopyroxene will react with a garnet and it will change the structure of the garnet. And when it will change the structure of the garnet, it will make some new mineral which is known as a majoritic garnet. This is known as a majoritic garnet, and majoritic garnet is also known as majorite. Okay. So, basically there is a difference in mineral formula in the garnet and in majorite. We will discuss about this in the next slide. So, but you should at present you just remember that when you go below the 300 kilometer, your garnet is not a stable phase. Garnet will react with a clinopyroxene and it will make a majoritic garnet, which is also known as a majorite. So, basically when you are at the bottom of the upper mantle from 300 kilometer to 410 kilometer, what you will observe that you mostly have a 3 minerals, and when you go deeper and deeper, these 3 minerals, that is basically your olivine 60%, then you have almost like a 35 or 30% of majoritic garnet, and then remaining 5 to 10% is your clinopyroxene. So, these 3 minerals are abundant mineral in the bottom part of the upper mantle. Then you go to the more deeper, when you go to the transition zone, which starts from 410 kilometer and ends at a 660 kilometer. But transition zone is divided also into 2 parts. So, basically you have a upper part of the transition zone and you have a lower part of the transition zone. So, these transition zones are basically divided by a 520 kilometer. So, the upper part is from the 410 kilometer to 520 kilometer depth. And what exactly happens here, if you see from 410 to 520 kilometer, if you draw one horizontal line from this depth. Okay. So, what you will observe that your transition zone, your this olivine, which is your orthorhombic structure, okay, which basically changes its structure. So, if your mineral or your compound has the same formula, but if it changes its structure, okay, so we call that particular mineral is a polymorph. Okay, polymorph. So, polymorph is derived from the polymorphism. It means that different forms or different structure. This is a poly means different and morphism means structure or forms. So, basically your this olivine structure will change to another structure which is called as a Wortzellite, okay, which is called as a Wortzellite, and their structure is changes. So, in 1950s there was a scientist, his name was Francis Birch. His name was Francis Birch, and he was working with, he was doing his PhD with, he was working with Professor Percy Bridgman in Harvard University. So, in 1950s he was trying to understand how the density changes inside the earth. So, basically that time there were lots of this seismological data was generated, and we have a real density data which varies with depth in the earth. And what he did, he calculated, he take a ratio of the density variation with depth in a real earth divided by the density of the earth variation with depth in adiabatic condition. So, he basically calculated this ratio and he named this ratio as a Boolean parameter, and when he calculated this Boolean parameter, he observed that this ratio is more than 1 for in case of the transition zone. So, if your Boolean parameter which is named after a very famous New Zealand seismologist Keith Bullen. So, if you take this parameter and if this ratio, which is a real density variation in the earth determined by the seismic observation, and then you calculate the density variation with depth in an adiabatic condition, if this is more than 1. So, in this case, if you in the earth's interior, if this ratio is more than 1, so he predicted, the Francis Birch predicted that this is basically because of the phase transition, and later when people did an experiment, when there was a development of the high pressure equipment in different parts of the Japan and in US. So, when people did some and also in Australia, people when they did an experiment, what they observed that there is some new phase is forming when they take the mantle composition, and when they compress it, the olivine is changes its structure. So, when you have this kind of situation, so there is a kind of phase transition, and it was first proposed by Francis Birch, and later it was proved by a experimentalist, and then later some of the natural samples have this kind of high pressure polymorphs of olivine. So, basically when you go to the upper part of the transition zone, your olivine will basically changes to another structure which is called as a Wurtzeliite, and this Wurtzeliite phase will be stable from 410 to 520 kilometer depth, and the proportion of this Wurtzeliite phase will be exactly same like your olivine. So, olivine in the upper part of the mantle is 16 volume percent is present. So, similarly Wurtzeliite is also 16% volume percent will be present in the transition zone. And if you see the remaining part of the upper part of the transition zone, you mostly have a majority garnet. So, you see when you slightly go deeper in the upper part of the transition zone, you will find that your clinopyroxene is no more stable. So, clinopyroxene will completely dissolve into your garnet structure, and it will make a majority garnet. So, basically in the upper part of the transition zone, you have a 60 volume percent of your Wurtzeliite and 40 volume percent of your majorite. Okay. In the just upper part of the transition zone, you have a 2 to 5% of clinopyroxene. So, when you go to the lower part of the transition zone, which starts from 520 kilometer to 660 kilometer depth. Okay. So, in this part, what will happen that the Wurtzeliite, which is a polymorph of olivine, this will change to the another structure. Okay. This will change to the another structure, and it will form a new mineral which is called as a ringwoodite. So, basically if you see the phase transition of olivine from olivine, which is a stable at the upper part of the which is stable in the upper mantle, and then when you go to the upper part of the transition zone, olivine will have a phase transition, it will form a Wurtzeliite which is stable from 410 to 520 kilometer, and then it will another phase transition will takes place from 520 to 660, that is a ringwoodite. So, basically there are some phase transition, and all this phase transition your mineral formula is same. So, you have this Mg Fe whole twice SiO4. So, this is a formula of olivine, and when you only the structure of this olivine is changing. And if you notice another thing in the upper mantle, so what you will observe that some of the phase which is denoted in this yellow part, that can be also stable at the lower part of the your transition zone, and this phase is called as a calcium perovskite, which is known as a calcium perovskite. So, if you see the, and all these minerals are basically a silicates, and we know that silicate is made up of silica tetrahedron, and in the silica tetrahedron the coordination number of silicon is 4. So, in the upper mantle, you have all the minerals, all the silicates present in the ultramafic composition have a tetrahedral coordination. So, four-fold coordination is present in the silicate mineral. When you go to the transition zone, you basically have a two different type of coordination of your silicon. Okay. So, you will have a silica will form a silicate, and these silicates will have a two different types of coordination. So, basically it will have a four-fold coordination, that will form a tetrahedron. So, your silicon atom is connected with a 4 oxygen, and then you have a 6-fold coordination. So, basically you have a silicon atom which is connected with a 6 oxygen, and you can think about the octahedron. So, basically you have a silicon which is present in the transition zone will have a 4-fold coordination and 6-fold coordination, but the olivine and its polymorph will always form in a 4-fold coordination. The 6-fold coordination will be present in your majority garnet. So, majority garnet silica will have a 4-fold coordination as well as 6-fold coordination. So, we will discuss about the structure of majorite in a few minutes. So, you just remember this, you just try to understand that the upper mantle you have a silicon which has a 4-fold coordination, and in the transition zone you have Si, that is 4 and 6-fold coordination. When you cross the transition zone and when you go to the lower mantle, so lower mantle basically starts from 660 to your 2900 kilometer. In this diagram it is up to 1000 kilometer, this diagram given. This is from a very good paper which is published in Elements magazine in 2005 by Dan Frost, and I borrow this diagram from that paper. And if you see the lower mantle, so there is a very interesting thing is happening in the lower mantle, and that is that most of the silicon present in the your lower mantle will have a 6-fold coordination. So, it will have a octahedral coordination. So, to compare to your upper mantle and transition zone, if a mineral, if a silicate is stable in the lower mantle, it will always have a octahedral coordination. What does it mean? That your silicon will connect with a 6 oxygen. Okay. So, your coordination number is changing. So, if you find a mineral and from some instrument, if you can calculate or if you can measure the coordination number, and if you see that the silicate in that silicate, the silicon which is present in this silicate has a 6-fold coordination, you immediately understand that this material is coming from your lower mantle. So, the coordination number is very important to know the mineral's properties and its structure. So, in the lower mantle most of the minerals are in the 6-fold coordination. So, if you see carefully the lower mantle, so in the lower mantle what you will see that if you draw a horizontal line, which is start from 660 to 700 kilometer depth. Okay. So, in this mineral what you will observe that the most abundant mineral in this part is this mineral which is called as a magnesium silicate perovskite. This is the formula of this mineral is your Mg FeSiO3. There are some other cations are also present, which will go to the different this structural site. But if you write down in a simplified way, your mineral, this is MgFeSiO3. The formula is exactly same like your pyroxene, but their structure is different. That's why it is called as a magnesium silicate perovskite, because its structure is close to a perovskite structure. And we know that the perovskite is a mineral that is your calcium titanium oxide. So this is a perovskite, and which is very abundant in kimberlite. In some other magma, other rocks, you can find this mineral, perovskite. So basically, if you see the most abundant mineral in the upper part of the lower mantle, you almost have more than 50%. Even sometime, if you take this one, this is 10% and this is your 90%. So you have 12% to your 92%. So almost like a 80% of the mineral, 80% of the lower mantle is made up of this your magnesium silicate perovskite. So this magnesium silicate perovskite has now a name, and we call this mineral as a bridgmanite. We call this mineral as a bridgmanite. So in the first lecture we discussed that how we name a mineral. So if a mineral is a naturally occurring, then we if some new mineral is discovered, so scientists mostly approach to the International Mineralogical Association, and then if that organization is convinced, so they name some new mineral which is found in a rock or in a some other natural occurring material, for example meteorite. So you see the upper part of the mantle, upper part of the lower mantle, you have a bridgmanite which is almost a 60 to 80% present, and then remaining your this 12 to 15%, you have a second most abundant phase, that is your ferropericlase. And then you have ferropericlase is structure is very similar to your salt structure, and then you have a magnesium, you have a majority garnet which is also present in the upper part of the lower mantle, and then you have a calcium silicate perovskite, which is a calcium rich perovskite, and the formula is CaSiO3. So basically these four minerals are present at the top of the lower mantle. When you go to the little bit deeper below 700 kilometer, you will find that your majorite is not stable below 700 kilometer, and then the lower part of the mantle is mostly made lower part of the mantle is mostly made up of your bridgmanite, which is 80%, and then you have a 12% of your ferropericlase, and then 5% is your calcium perovskite. So these three minerals are quite abundant in below 700 kilometer in the lower mantle, and then these three phases will exist up to a 2700 kilometer depth, because our lower mantle is up to a 2900 kilometer depth. So last 200 kilometer depth you will have another transition, and that transition is known as a post perovskite transition, is known as a post perovskite transition. So basically whatever bridgmanite we have, so bridgmanite will change its structure, and this is new structure will called as a post perovskite. Okay, so your mineral formula is the same, but your structure, the mineral will produce a new crystal structure. So you see in the earth's mantle you have several this polymorphic reaction. So, there are different minerals which form a new mineral, and their crystal structure are completely different, but their mineral formula is same. For example, we already discussed about the olivine, and then we have a bridgmanite also. So, these are the some of the minerals which are stable in the ultramafic part of the mantle. If you see the crystal structure, because olivine is stable in the upper part of the mantle. So, if you remember the general formula of olivine, so generally in the olivine we write down the formula is MgFe whole twice SiO4. So, you have a mostly in olivine you have a magnesium and an iron. So, because both these atoms can exchange each other because their atomic radii is very similar. These are magnesium is 0.72 angstrom and iron is 0.78 angstrom. So, they can exchange each other easily in the crystal structure in the lattice. So, and mostly they have a 6-fold coordination. So, it has a 6-fold coordination, and then you have a silicon which is a 4-fold coordination. So, and if you see the density of the olivine, this is 3.32 gram per centimeter cube. So, this is the structure of olivine. So, in this structure, olivine, the structure of olivine is projected perpendicular to the a axis. Okay, so you you imagine this projection is perpendicular to the a axis. So, sometime in other books you will find that projection is in the different axis. So, it can slightly, the diagram can rotate. Okay. So, if you see this diagram, so olivine is also known as a alpha phase. Okay, it is also known as a alpha phase, and these are nesosilicate. So, nesosilicate, the definition of the nesosilicate is that you have a isolated your silica tetrahedra. So, basically your silica tetrahedra will not connect with another silicon tetrahedra. So, if you see this image, you will find this blue color, this tetrahedra. So, it is projected in a 2 dimension. So, that is why it looks like a triangle, but these different triangles are basically a sides of the tetrahedron. So, you have these 3 sides, and then at the base you have another side. So, basically you have 3 faces. So, all these triangles are indicating a faces, and if you see, there are 2 different kinds of this tetrahedron, one with a solid line and another with a dotted line. So, when you have a solid lines inside this triangle, so it means that this tetrahedron is pointing upward. Okay, so towards the screen. Okay, and if there is a triangle, and inside triangle if you have a dash line, for example this one, so it means that your tetrahedron is pointing downward. And if you see that these two tetrahedra are not connected with each other, so they are isolated. And if you see this general formula of your this olivine, so it has a 2 octahedral side, which is indicated in this diagram by a M1 and M2 side. So, you see you have a 2 M1 and M2 side. So, if you see that this M1 and M2 side carefully, what you will observe that M1 is relatively smaller in size and M2 is relatively larger in size. Okay. So, if I ask you that if you have a magnesium and if you have an iron atom, which atom will prefer to the M1 side and which one will prefer to the M2 side. So, because M2 side is larger in size, so larger atom will prefer to the M2 side. So, your iron, which is larger in compared to magnesium, so it is will prefer mostly in the M2 side. And if you notice this in this diagram, you will observe that in the larger side are basically the corners of this larger side M2 side, which is the octahedral side. So basically you have 8 sides, and this octahedral side, the corners, the oxygen present at the corner of this octahedron are connected with a tetrahedron. So in this kind of structure in olivine, your oxygen in the tetrahedron side will always connect with a M2 side. Okay, so you see the another oxygen is connected with another M2 side. Okay, but if you see the M1 side, so M1 side is basically connected along the edges. So you see that there is a connected along the edges. So if you see the oxygen which is present along the this edges, so if I change the color, so so if you see there are two oxygens that are present along the edges of this M2 side and M1 side, and they basically share the oxygen. So these are some oxygen which are basically bridging together in the octahedral side, and in the M2 and M1 octahedral side will be always shared by the edges. So edges are shared here because the net charge here is 4 minus. So you have a net charge is your 4 minus because you have a 2 oxygen atom and each atom has a -2 charge. So the net charge is -4, but the point here is that if you see the center atom which is present in this M1 and M2 side, which has a relatively larger valency. So at the center of the M2 side you have a Fe2 plus, and here you have a Mg2 plus. So basically the charges of this smaller cation is relatively small compared to the whatever present in the your tetrahedron. So in the tetrahedron you have a silicon, so which has a larger valency and charge. So silicon is 4 plus. So basically the repulsion between these two atoms will be small. So because of that, this kind of structure will be stable along the, if they are sharing the edges. And if you notice this in this diagram, what you will observe that your basically this M1 side which is more distorted than a M2 side. So smaller M1 side because they are connected by the edges. So you see there is another this another side is connected with your M2 side. So you have basically this M1 side which is joined by two different edges. So because of that, it has its structure is this octahedron is distorted compared to your larger M1 M2 side. So this is about the structure of the olivine. And if you see the probability to place iron and magnesium in M1 and M2 side at high temperature, the probability is equal because it can go to the any of the side because their sizes are relatively equal, the atomic radii is very close to each other. So at high temperature, M1 side iron can accommodate, and in M2 side magnesium can accommodate. So this is about the structure of the olivine, which is the most abundant mineral in the upper mantle. If you see the second most abundant mineral in the upper part of the upper mantle, that is the garnet. So we write down the formula. General formula is your X3 Y2 Si3 O12. And if you see this formula, what you will observe that here in X side you mostly have a divalent cation. So you have a 2 plus charge cation. For example, you have a magnesium, you have a iron 2 plus, you have a calcium 2 plus. So all this cations can accommodate in the X site, and the coordination number of this X site is a 8-fold coordination. So basically it has a 8-fold coordination. If you see the Y side where you have a 3 plus cation, so trivalent cation can accommodate in this Y side. So you have a aluminum 3 plus or chromium 3 plus or iron 3 plus. All these elements can accommodate in the Y side, which has a 6-fold coordination. So you have a 6-fold coordination. And in the Si side, that is a G side, you mostly have a silicon, and silicon has a 4 plus charge, and it has a 4-fold coordination. So I told you that most of the silicate which is present in the upper mantle has a 4-fold coordination. Say silicon has a 4-fold coordination. So your garnet, which is present up to 12 to 15 volume percent in the upper mantle, in the upper part of the upper mantle, has this general formula. And if you see this diagram, what you will observe that it has a 3 different structural side, and it has a 8-fold coordination, it has a 6-fold coordination, it has a 4-fold coordination. So if you have a 4-fold coordination, you basically form a tetrahedron. So if you see, you will find there are some tetrahedron, and this red color sphere or circle is basically your oxygen atom, and at the center you have a pink this circle, that is your silicon. And then if you have this kind of arrangement, so this is your tetrahedral coordination. Then if you see, there are some other tetrahedral coordination you can see. So basically these are connected with your 8-fold coordination. So if you see, there are some distorted cube here, so you have some distorted cube here. So basically this distorted cube have this 8-fold coordination. So at the center you have this A cation, so basically it will go to the X side. So these are basically your Mg2 plus or Fe2 plus or calcium 2, any divalent cation can go here, and it will have a 8-fold coordination. So if you see, the Y side, which is your cation B, will go in this diagram. So in this one you have a trivalent cation. So basically this is your octahedral side, octahedral sides, okay, and this is your 8-fold coordination in case of magnesium, iron and calcium. So here you have a aluminum 3 plus, Fe 3 plus and chromium 3 plus. So if you see this diagram carefully, what you will observe that in this diagram, this 8-fold coordination in which the center you have a magnesium or divalent cation is in this one, this is connected, the corners or edge is connected with a 2 tetrahedral side, okay. So you have a 1 tetrahedral side is this one and another one is this one. So in one tetrahedral sides only corners are connected, and another tetrahedral sides your edges are connected, okay. So when your corners are connected, your only corners are connected, so this particular tetrahedral side are more rigid because it will not form any deformation in this structure. But if you see this tetrahedral side in which the edges are shared, so this is more distorted. So it is not very rigid, it is distorted. So this tetrahedral side will be distorted and this will be less distorted. And if you see, the octahedral side also shared by the sharing is happens in the along the edges. So you have a octahedral side in which you mostly have a aluminum, chromium or Fe3 plus. So you have some sharing along the edges of the your cube and the octahedron. So this is the structure of the garnet, which is the most abundant mineral in the your upper part of the upper mantle. If you see the another mineral which is the most abundant in the upper part of the mantle, that is almost like 20% or a little bit less or more depending on the pressure. So you have that is pyroxene. So pyroxene, when we talk about the pyroxene, the general formula of pyroxene is your X2 Si2O6, okay, and your X side will be mostly your magnesium, iron and calcium, and this will have a 6-fold coordination, and then you have a silicon which has a 4-fold coordination. So this is the crystal structure of your pyroxene. So if you see in the pyroxene, you have a 2 octahedral sides. So you have a M1 side and you have a M2 side, and M2 side is larger. So M2 side is so you have a M2 side which is larger than your uh, M1 side. So if you see the placement of this octahedral side in the crystal structure of your pyroxene, so what you will observe that the larger M2 side is placed in between the bases of the tetrahedra. So if you see that there are some tetrahedral side, there are some tetrahedral sides, and in between the base of this tetrahedra you have a larger M2 side. But when you have vertices of this tetrahedra, so you have a vertices of the tetrahedra. So smaller sides are placed in between the vertices of the two tetrahedra. So why is that? Because if you see the net charge at the base of the tetrahedra, so you have a quite large net charge at the base of the tetrahedra, because the number of oxygen is more at the base of the tetrahedra. But in case of the vertices, you have only each vertex have a one oxygen, so the net force here is relatively small. So the repulsion will be less between these two vertices or these two sides. So basically you have a smaller space, but here the repulsion is more. So because of that you have a more space and you can put a larger octahedral side here, and because of that you have a M2 side, and here you have a M1 side. So this is about the structure of the pyroxene. So in case of orthopyroxene, if you take a example of enstatite, where you have a M1 and M2 side, but in both the sides you have a magnesium atom, so your M1 and M2 will be the same. But in case of diapside, where you have two different octahedral side M1 and M2, and both this cations will go to the different this sides, so you have a larger M2 side and smaller M1 side. And if you see this kind of arrangement, so this is basically you have a octahedral, tetrahedral, octahedral, and you have a TOT, this tetrahedral, octahedral and tetrahedral, this arrangement. And basically your octahedral side is sandwiched between your both the two tetrahedra. So this is a TOT kind of structure, and if you see this structure carefully, so there will be some kind of uh, uh, some kind of cleavage will form, which will along this gaps between this tetrahedral sides, and this will be exactly at a 90 degree. So close to 90 degree. So it is 92 and 88 degree. So that is a very characteristic for your pyroxene. So if you try to identify a pyroxene, if you find the set of cleavage that forms almost at 90 degrees, so we say that this is a pyroxene compared to the amphibole. So this is the crystal structure of your pyroxene. And if you see the another major phase which is present in the lower part of the upper mantle, that is the majorite. So if you write down the formula of majorite, so the classic formula of majorite has a your Mg3 Mg Si and then SiO4 whole thrice. So basically if you compare with a garnet structure, so in the garnet structure I said because garnet is stable in the upper part of the mantle. So, garnet has a just four-fold coordination. So, here your silicon has a four-fold coordination. But if you see the majoritic garnet, so majoritic garnet your silicon is mostly present in the four-fold coordination, but when it reacts with the clinopyroxene, what will happen that your silica proportion will increase. In the garnet, if you write down the formula X3 Y2 Si3 O12, so basically you have a three silicon atoms in the pure garnet structure. But if you write down the formula of your majorite, which is basically X3 Y2 minus X and Si3 plus X O12. So, basically you are increasing the proportion of silicon in the majority garnet. So, in the majorite you have always more than 3 silicon atom. So, if you see this, when you have more than 3 silicon atoms, so with pressure this proportion of silicon will increase in the majorite, and your this tetrahedral coordination silicon will change to octahedral coordination, and because of that some of the silicon will go to the octahedral coordination. And if you see the if you see in the in your garnet, if you go back to the last slide. So, in the garnet you have a 8-fold coordination, that is magnesium is present, but here if you see the structure you have a magnesium that is a 6-fold coordination and also 12-fold coordination. So, basically you have a 3 different structural site, and in this structural site what you will observe that you have a 12-fold coordination magnesium, and then you have a 6-fold coordination in which silica and magnesium both will go, and then you have a silicon which will go only to the your 4-fold coordination. And this phase majorite is stable from 250 kilometer to 700 kilometer depth, and this phase was first synthesized using an experiment, and later it was found in a meteorite, that is a very famous meteorite. It is known as a Currara meteorite. This is a L6 chondrite meteorite, and it was found in a western part of Australia. So, if you see this structure, this is a crystal structure of your majorite, and basically you can find there are some spheres, some orange spheres. So, these orange spheres are your 12-fold coordinated coordinated atoms, and then you have basically you have two different colors of octahedron side. So, two different color of octahedron side, this is octahedron side this, and then you have this orange color octahedron, and then you have some this tetrahedron side. Okay. So, that is from the blue color. So, these are the your different structural site. So, if you see the 12-fold coordination, in the 12-fold coordination your magnesium will be present, and in case of your blue octahedron, so which is this one. So, here you have a silicon, and then you have a orange octahedron. So, that one you have a Mg2 plus, and then you have a blue tetrahedron where you have a silica. So, this is about the majorite. So, I will stop my lecture here, and tomorrow we will discuss more about in the next lecture we will discuss about the minerals, the crystal structure of the minerals which are present in the transition zone and in the lower mantle. Thank you.